Hi, I'm Jeongyoun. I will be presenting partially observable task and motion planning with uncertainty and risk awareness. In open-world environments, robots rarely have complete knowledge about their surroundings or the dynamics of the world. Because of this, robots must make decisions while dealing with uncertainty. For example, object locations may be noisy, some objects may be occluded, and physical interactions can behave unpredictably. If a robot ignores these uncertainties, it can easily produce unsafe or catastrophic behaviors. Therefore, when robots plan their actions, they must explicitly reason about risk and uncertainty in the environment. However, in real robotic settings, predicting the exact outcome of an action is extremely difficult. Due to stochastic dynamics and partial observability, executing the same controller can lead to different outcomes each time. Traditional task and motion planning, or TAMP, typically assumes deterministic action outcomes and fully observable states. But when we move to realistic settings where uncertainty exists, planning must instead operate over belief states, which represent probability distributions over possible world states. Unfortunately, planning directly in these belief state control MDPs become computationally intractable due to enormous states and action spaces. To address this challenge, the paper introduces Tempora. Tempora extends task and motion planning to environments with partial observability, stochastic outcomes, and imperfect symbolic control models. The key idea is to use coarse symbolic descriptions of controllers, including their conditions and possible effects, to control a sparse MDP representation of the planning problem. This allows the systems to perform uncertainty-aware planning efficiently using probabilistic planners such as LAO. The authors evaluate the approach across multiple uncertainty scenarios and real robotics tasks, and demonstrates significant improvements over reinforcement learning, Monte Carlo research, and previous belief-based TAMP methods. The key challenge is that the belief space MDP is extremely large and continuous. To make planning tractable, Tempora introduces belief state abstractions. Instead of reasoning over full probability distribution, belief states are represented using symbolic propositions. For example, the robot may reason about whether the pose of an object is known with high probability or whether the robot's hand is free. These logical predicates summarize important aspects of the belief state. By representing belief states with these propositions, the system constructs a compact abstract belief state MDP. Using this abstraction, the Tempora planning processes proceeds in several steps. First, the continuous belief states is converted into symbolic propositions through belief abstraction. Next, controllers are modeled as operators that include preconditions, deterministic effects, and uncertain effects. Using these symbolic descriptions, the system constructs a sparse abstract MDP that captures the important transitions in the task. Finally, this abstract MDP is solved using a probabilistic planner such as LAO, producing a policy that selects the next control while considering both risk and uncertainty. However, another important challenge remains. The symbolic operator descriptions only specify possible effects, but they do not include the probabilities of these outcomes. To plan effectively, the robot must estimate these transition probabilities. These probabilities can be learned through simulation, but this process can be extremely expensive because it may require geometric reasoning, precision queries, and physics simulation. Therefore, naive random exploration of the transition space is highly inefficient. The goal is to learn only the task-relevant transition probabilities efficiently. To solve this problem, the paper introduces a Bayesian optimistic exploration strategy. Each transition probability is modeled using a beta distribution, which represents uncertainty over the probability of a particular outcome. When simulators are performed, the model updates the counts of successes and failures. The system then uses a Bayesian upper confidence bound criterion to guide exploration. This encourages the planner to explore transitions whose probabilities are still uncertain while gradually focusing on the most promising actions. The model learning process follows an iterative loop. First, the system generates candidate plans using a determinized planner. Next, it selects transitions with higher uncertainty based on entropy. Controllers are then simulated from belief states to observe their outcomes. These observations update the transition counts and probability estimates. Using the updated information, the system constructs a sparse abstract MDP that captures the relevant dynamics of the task. Additional techniques such as progressive widening allow the system to handle continuous parameters, and the system can also automatically identify belief conditions that influence controller outcomes. Finally, the authors evaluate tempera across several robotics tasks involving different types of uncertainty. The table shows the average discounted return for various planning and model learning strategies across these tasks. Tempera consistently achieves the best or near best performance. These results demonstrate that combining symbolic abstraction with Bayesian model learning enables efficient and robust planning in uncertain robotics environments.